Okay, welcome to the second session of the day. We start with Hugo. He's going to talk about strong pseudomonads and premonoidal bicategories for us.
Thank you. Thank you, yeah. So this is work with Philip Saville, who is sat over there. And the main contributions are these two new notions of strong pseudomonads and premonoidal bicategories, which are intended to be useful in the semantics of programming languages. If you already know about strong monads or premonoidal categories, then this is just the, or is what we think is the correct extension of these concepts to bicategories. But if you don't, I'll explain what they are in the talk. So it's just a quick reminder on strong monads. So a monad is an endofunctor on some category C, equipped with two natural transformations, mu and eta. And the idea for strong monads is we want to combine the monad structure with a monoidal structure. Often it's a product structure, but in general it's a monoidal structure on the category C. So I've written out the whole structure because I'm going to reuse this notation in the talk. We have a tensor product, a unit object, and then some weak associativity and unit constraints. So strength for a monad is a natural transformation of this type, A tensor TB to T of A tensor B, which should be natural in A and B. This is a left strength. There's also a corresponding notion of right strength. And this natural transformation has to be compatible with both the monad structure and the monoidal structure. So what that means is this, the details of the diagrams don't really matter, but I just thought to include them. And in any case, skip they don't matter. Okay, so this is the strength being compatible with the monoidal structure. You can see here the unit for the monoidal structure and the associativity. And it should also be compatible with the monad structure. So there are two more diagrams for T being compatible with mu and eta. I just give some motivation for strong monads in the context of programming languages. Usually in semantics, we use a category as our basic semantic model where the objects are types and the morphisms are programs. And the idea of having a monad is we can model computation with side effects. So TA might just be a type of computations that can return values in A, but they can also do other things like be probabilistic or print something. And so what we do in semantics is we describe the semantics of a whole program in terms of the semantics of the small parts. That's what we call compositional semantics. So I think this is all well known, but I'll just say it quickly anyway. If we have a term n, in some context gamma, and n has type B, we can pass n as an argument to another program m using essentially the Kleisli composition for the monad T. Okay, here m is parametric in the value x of type B. But in general, if we want to do this for arbitrary n and m, we need a strength because n has the same type as before, but now m has a parameter b, a parameter x of type b, and another parameter y of type a. And so m is now a morphism of this type, a tensor b to tc. And so if we want to compose n and m, we start with a tensor gamma, we apply n to get a tensor tb, but then in order to apply tm, we need to pass the a into the monad somehow. So that's the point of the strength. Now some motivation for bicategory. So recently in semantics, there's been a lot of models coming up that form bicategories and not categories, meaning that the composition of morphisms is not strictly associative. And the unit, the identity is also only a weak identity. I've put some examples on the slide. So examples include bicategories of spans, where you have some base category and then a morphism between A and B is like a span from A to B, and then you compose them by pullback. And so then if you try to look at what associativity means, you have to compare this span and this one here, these two ways of taking pullbacks, and in general they're only isomorphic, they're not equal. It's not as weakly associative. Then in game semantics, this comes up a lot as well. This is just a picture of a strategy in game semantics, just to say that this is a morphism. It's a kind of structured object. And when we compose, we also have to perform some kind of universal construction. And so we get the same, for similar reasons, a weak kind of associativity. And something else that comes up is this para construction, where the morphisms from A to B are now some parameter space B, and then a parameterized function of this type, A tends to P to B. And so then when you compose, you have to deal with this associativity and so on. Okay, the problem was that we wanted to combine these new models with the existing theories of program semantics using strong monads. And there was no notion of strong monads for bicategories. So there's a notion of monads, which is a pseudomonad, but there was no notion of strength. And that's why we started looking at this work. So the talk, I'll just give you the definition, which is going to be kind of, I don't know, it's a technical definition, I guess. But the main message of the talk is to explain why this is the right definition, and the argument is that it corresponds to another well-known notion, which is that of an action. So I'll explain this in the second part of the talk, and I'll get to premonoidal bicategories, which are kind of more general way to give semantics to programming languages with effects. Right, so in bicategory theory, quickly, basically, everything is now weak. So whenever in category theory we would say this diagram commutes, we now have a two-cell, which is supposed to be an isomorphism of morphisms that says that represents the commutativity of the diagram we had before. So as an example, a pseudo-natural transformation between functors between bicategories consists of, as before, components for every object, but also normally we would say this diagram commutes for every f, for every morphism of the category. And now we just say we ask for this extra two-cell for every f, and then this has to now satisfy further axioms. For example, if I take the cell for f and the cell for g, this should be equal to the cell for gf. Okay, modulo the fact that f and g might not preserve composition exactly, but yeah, just simplifying a bit. Okay, so everything in bicategory theory is like this. For example, yeah, in this case, they are normally, when we say pseudo, that means invertible, but there'll be notion of lax natural transformations or plaques, which is when they're not.
So I've heard it usually weak is just exists a natural transformation, strong or pseudo is isomorphism, and strict is when it's equality. So that's kind of what I've grown accustomed to, but yeah.
Right, yeah, okay, yeah, weak or lax, I think, is a standard.
But you used the word weak to talk about this isomorphism.
Oh, sorry, I said weak, yeah, in a vague sense, just to mean everything is not strictly, yeah, that's, okay, I guess everything is strong in your terminology, and not strict. Thanks. Right, so, I mean, this shouldn't be surprising if you've seen monads and bicategories before. Now, I've just filled every diagram that you normally require for these things with a two-cell, and these will need to be invertible. And so all of these then satisfy a bunch of coherence axioms that I don't include because there's a lot of them. But that's the idea. And so for strength, again, this should be unsurprising, at least to this point. Strength for a pseudomonad is a pseudo-natural transformation, just like before, compatible with the monoidal structure and the monad structure. So we have two cells, invertible, and we came up with these axioms, which we think are the right ones, that look like this. So, this is really just to flash the axioms, but basically the pink cells are the monoidal structure, and this should be compatible with the new strength structure. And similarly, I think the blue ones are the pseudomonad structure, and they have to commute in some ways with all this new data. Okay, so I mean, this isn't very convincing because I could have just drawn anything. So I'll just try and explain what makes these axioms correct. And to do this, I'm relating to this notion of strength with the notion of action. And this is something that you can also do in the categorical, in this plain categorical setting. But so everything here is going to be bicategorical. So we're looking at actions of monoidal bicategories. So B is a monoidal bicategory. And we're looking at actions of this on the Kleisli bicategory for T. Okay, so this is going to be a functor of this type. And the first point is that whenever you have a strength, you get an action, which is defined in this way. On objects, you just take A and B to A tends to B, which is still an object of the Kleisli bicategory. And on morphisms, you take F and G of this type, you take their tensor product, and then you apply the strength. And this is a morphism in the Kleisli bicategory. Okay, and the same kind of thing happens on two cells. And you can go back if you start with an action and you assume that on objects is just the tensor product, then you can recover the strength by applying the action functor to these two, to the identity on A and the identity on TB, which you view as a morphism from TB to B in the Kleisli bicategory. And that gives you a morphism of this type, which you take to be the strength. You have to check everything works, but that's the start. And I want to explain a bit more, so I was a bit vague here about requiring that the action on object is exactly the tensor product, so there's a slightly more technical thing to say, which is based on this notion of extension. The first observation is that the monoidal structure is a canonical action of B on itself, okay, where all of the monoidal structure, all the other structure, corresponds to what you need for an action as well, so the associativity and so on. And we look at extensions of this canonical action to the Kleisli bicategory. So that consists of an action on the Kleisli bicategory, together with all this data that you need for an action, together with a transformation of this type. So this is like, if I start with two objects A and B, I take the tensor product and I embed in the Kleisli category, and or if I embed and then act, these should be isomorphic. But actually, we ask for not just an arbitrary transformation, but what's called an icon, which is a transformation where every component is the identity. Okay, so in category theory, that's just trivial. So because all we have is these component morphisms, but here we have two cells as well for a pseudo-natural transformation. So these don't have to be the identity. So what it means is this is now a naturality square, except two of the sides have been collapsed. So we have for every F and G, we have a morphism, a two cell of this type. And then we're going to ask that using this two cell, all of the structure for the action is related to the structure for the monoidal structure on B. So we have extra axioms that look a bit like this. Okay, the red things are, this is for the action, this is for the initial monoidal structure, and then you pad out with this new blue thing just to say that they match up. Right, and this is the main theorem, which is where the definition of a strength comes from, is that for a fixed pseudomonad on a monoidal bicategory, there is an equivalence of categories between a category of strength, or I should say left strength for the monad T, and a category of extensions of the canonical action to the Kleisli bicategory, just like I had on the previous slide. And of course, there are morphisms now between strengths, because we can define two cells that commute with all the data. Yes?
Does this work at the categorical level?
Yeah, that's right. It's just a bit more straightforward, because so it would be an isomorphism of sets, not a yeah. So all of this comes from the generalizing a well-known result. That's right. Which actually is why we take it as justification that our notion is correct. Okay, and so this is all for left actions and left strength, but there's a corresponding result for right action and right actions and right strength. And in fact, we have some more work on proving that if the monoidal category is symmetric, then whenever you have a left strength, you can canonically derive a right strength. And they're compatible in some ways. Often in semantics, people use bi-strong monads that are kind of compatibly left and right strong. But this isn't it's not in the talk. Okay, so this is the final part. So in the semantics of effects, of programming languages with effects that use monads, you have to keep track of the monad everywhere. So you have T, you use Kleisli composition and so on, which arguably is a bit indirect, because sometimes in the programming language, in the syntax, there's no explicit monad, there's just programs and effects. And so, so some people, so in the 90s, John Powell and Edmund Robinson have axiomatized the structure of the Kleisli category directly, and that's known as the premonoidal category, as a category that has a tensor product on objects, but that it's not a functor of two arguments. So you don't have the usual interchange law that you have in monoidal categories. What that means is if I have M from A to A prime and N from B to B prime, I can't do M and an N. I can't swap the order that I do M and N in. I think I was, yeah, so this is the string diagram notation, I guess. You can't just swap the order of things, which makes sense if a program is doing something like printing on the screen. Of course, you can't reorder the statements because you might get a different effect. So in general, if T is a monad, then the Kleisli category doesn't have this property. Right. So instead of having a tensor product as a functor of two arguments, you have families of functors of this form for every object A. But there's a subtlety, which is that all of the structural morphisms in the monoidal category, so the associativity and so on, they should still satisfy interchange. Okay, in certain morphisms, you really care that they do satisfy the interchange law. And so the key notion is the notion of a central morphism. So I'll just give the categorical definition and I'll explain how we generalize it to bicategories. In a category with these families of functors, we say a morphism F is central if it just commutes with every G in the two possible ways. So this is the way where F is on the left, and this is the way where F is on the right. Okay, so it's left central and right central, I guess, for every possible G. And so when you define a premonoidal category, you say, okay, it's a category with these functors and then some central, natural, structural isomorphisms and so on. But of course, in bicategory theory, we diagrams never commute, and so you need to make these two cells. And I think so. This wasn't completely obvious. The way that we decided to do it is to notice that this is like a naturality square for this functor blank tensor F, I guess. And so what we ask in a bicategory with these pseudo functors is that a central morphism is now a morphism equipped with these two families of two cells that are pseudo-natural transformations in G. Okay. And so given this, we can define a premonoidal bicategory as exactly what you expect. So a category with families of functors A tensor blank and blank tensor A for every A. Central, so associativity, and unit pseudo-natural equivalences, which are equipped with central structure. And then, there's more data and axioms, but everything else is just like in a monoidal bicategory. And the main theorem, or the main justification for why this works is that if you have a pseudomonad that's strong on the left and on the right in a compatible way, or equivalently if it's strong on the left and the category is symmetric monoidal, bicategory is symmetric monoidal, then the Kleisli category is premonoidal in a canonical way. Okay, so I mean the main conclusion is that we have these new structures for dealing with effects in setting semantic models where composition is not strictly associative. And there's an interesting point which is different from the usual categorical story, which is that and I didn't talk about this in the talk, but if you have a premonoidal category and you restrict to the central morphism, to the central morphisms, you end up with a monoidal category because everything commutes with everything else, and that's what. So the interchange law holds. But here, if you define a bicategory of central morphisms, it's not really a sub bicategory because you have all these extra data on one cells, and so trying to make that monoidal seems impossible. So we have, we have some ideas for dealing with this, but really the direction is that of Fried bicategories. Fried categories are a way to have a premonoidal category with a chosen subcategory of central maps. So that's what would supposedly work here. Yeah, I'll stop now. Too short. Yeah.
Yeah, for examples of some effects that generalize to this bicategorical, like some normal effects. The idea that the normal computational effects that happen in the one categorical setting should mostly generalize to this setting, or?
Yes, it depends what you mean by normal. Some of them.
People usually use them for like failures and printing, like you said, and things like this.
Yeah, so say if you're in a Cartesian closed bicategory, you have like a continuation pseudomonad and a state pseudomonad and so on. And that does generalize. Really, the interesting applications that we have, or certainly that I had in mind, were in game semantics and models of linear logic, where the monad structure is a bit less obvious. So we had this theory of dialogue categories, which is supposed to be a way to look at game semantics in a monadic style. And that's what I was interested in dealing with.
So you have all these complicated diagrams. And I'm wondering, if you use instead of monoidal bicategories, if you use gray monoids, wouldn't that just make your life so much easier?
Yes, maybe, but then it wouldn't include the examples. Well, because the actual examples we have in practice, they're not gray monoids.
Yeah, but you can. You have stratification theory, right? So, diagrammatically reasoning in gray monoids.
Yes.
You're always using coherent status to write down the diagrams. That's where coherence is making the diagram full type. But your structure, you're trying to define a pseudo structure. Right? So you could define a strict version of a two-monad, right? But you still want the string to be pseudo. And so you still need all those two cells.
Yeah, so actually, I don't know if it would make our life simpler because, you're right. So at the moment, all these diagrams I had, they already assumed that they'd already pretended that a lot of things was strict.
That's just a hunch, but you could just make that explicit by saying that you're actually using gray monoids. Okay.
No, it's a good point. I'll have to think about that a bit more. Thank you.
So have you fully fleshed out some examples, non-trivial examples of this, or is it still a work of progress?
So we looked at these dialects. I mentioned game semantics, but we looked at this. So with the bicategory of games, which is not completely obviously an instance of some general thing. And then you have to write down what the monad does. And you have to show it's strong by hand, kind of. And so, that's what we did, I guess. The effects are never going to be completely new because everything is up to ISO is whatever we had before, if you see what I mean. So any example that you see is not going to be. It's never going to be completely in a computational sense. It's not going to be new, really. It's going to be the same. The same as before, up to ISO.
So what if you weaken these isomorphisms into just to be natural transformations or just to be two cells? Can you still get something useful out of it, or will there be
not to be invertible? You mean?
If you drop the inverted
Yeah, I don't have any examples, but yeah, I guess I don't know basically.
General theory kind of you still
Yeah.
constructions much work and
Yeah, I would expect a correspondence between lax strength and lax actions. You just have to be careful which direction each thing goes. But yeah, but because we didn't have any applications, I don't really. Yeah, it's a good point.
Okay. More questions? Let's take this.